Welcome back to Electronics. This is Dr. Ferry. This particular lesson is a review of Kirchhoff's laws. In a previous lesson, we reviewed linear circuit components such as resistors and capacitors and inductors. In this one, we're going to go through more detail of Kirchhoff's current law, or KCL, Kirchhoff's voltage law, or KVL. Kirchhoff's voltage law states that the sum of voltages around any closed loop is zero. Now, we show an example of a closed loop here. And in order to apply this, we would have to know what these voltages. So suppose this is V sub D, V sub A, V sub G, and these are all measured in volts, and this is V sub H. So I want to do a sum up the voltages around here. Now, if I'm sum the voltage from this point to this point, so I'm looking at the voltage potential, I actually gain voltage from this point to this point. But when I do a voltage, Kirchhoff's voltage law, I want to make sure that I'm always consistent with the way I use the polarities. So I use a little trick in doing this. I use the trick and say, if I'm going to be summing in this direction, if I come to a plus sign first, I add it. If I come to a plus sign here first, I add it. In all these cases, I come to a plus sign first if I go around in this direction. So I'm going to add these all. If I were to come to a minus sign first, I would subtract it. That's just my trick in making sure I get the polarity right. So starting at this point, I would have V sub H plus V sub D plus V sub A plus V sub G all have to sum to zero. And that's going to be true of any loop. It'd be true of this loop, it'd be true of this loop, any closed loop. Now I'm going to have you do a KVL quiz here. So looking at this circuit, I want you to find VH. Now coming back to the solution here, find VH, I want to do a KVL. Well, I can do a KVL around this loop, but I don't know what this voltage drop is. So let me do a KVL around this loop right here. And the way I do a KVL is in the direction I go, if I hit a plus sign first, I add it. If I hit a minus sign here, as in this case, I would subtract it. Now, it's not strictly physical because actually I'm losing potential as I go from here to here. But it's just a trick that I use to keep my polarities correct. So going around here, starting with plus VH, and then I get to the minus 2. Over here, I get a plus minus 1. And then around here, I get a minus 5, and then plus 4 equals 0. So when I add these up, let's see, I'm going to have a minus 8 plus 4. In other words, solving for it, I get a 4 volts. Now let's look at KVL in parallel circuits. So I've got these two elements that are parallel to one another, and that's the only thing in this circuit. So if I do a KVL around here, and this is V sub A, and this is V sub B, going around here, I would have, in this direction, V sub A minus V sub B, because I hit that minus sign first, is equal to 0. In other words, V sub A is equal to V sub B. And that is true anytime we've got two elements that are in parallel with one another. They're going to have the same voltage drop as long as you've defined them with the same polarity. So any two elements that are in parallel with one another have the same voltage across them. Now this is a numerical example, an actual circuit example with resistors in there of a KVL. And I'd like to be able to solve this and do, for example, a Kirchhoff's voltage law across this. So let me write this. There's lots of loops I could do. And do this loop right here. I can do this loop up here. So let me write a Kirchhoff's voltage law around here. So I would like to be able to write, so I'm going to do it around here. I'll need to be able to mention or write an expression for the voltage drop across this resistor. Now, by the convention, we show that resistance goes into the plus side in order for us to be able to use Ohm's law. So we'll call that V sub 1. So if I want to go around here, I hit the minus sign first, minus 10, plus this voltage drop here, V sub 1, plus V0, and that's all I've got on this loop is equal to 0. So V sub 1 is equal to I sub 1 times 20. V sub 0 is equal to I sub 2 times 10. And this is by Ohm's law. So now I've got an expression that I can use to solve for these variables here in terms of the currents. I can also do a loop around this way. Suppose I do this loop around here. So in this case, I hit the plus sign first. So it's plus 2 minus V0, because I hit that minus sign, and then plus this voltage drop. Well, remember the current goes into the plus side, plus I3, 5 is equal to 0. So I have another expression, and V0 again is equal to I2 times 10. So what we've been showing here is how to write KVLs for a particular circuit, an actual circuit, that we're making use of Ohm's law for that. Kirchhoff's current law says that the current entering a node equals the current leaving a node. For example, suppose I've got this current. This is a node right here, and this is a node because everything here is connected. So this is a node there, and call this I sub A, and this I'll call I sub B, I sub E, and I sub D. So if I do KCL at this node, I would sum up everything entering, and that would be I sub B plus I sub D is equal to the sum of what's leaving, I sub A plus I sub E. And that's true for any node. So I've got a node over here, and a node over here, and a node over here. It's true at every node. So in this particular case, we look at, for example, if we draw the current, if I've changed the directions. So now this one, I'm showing this way, this way, this way. Now what's entering is I sub A plus I sub B. What's leaving is I sub D plus I sub E. So if I change the arrow, the reference of my current, I have to just be careful that I'm consistent with it. Now if I have two elements in series with one another, then all the current, this is a node between them, the current entering has to equal the current leaving. So if this is I sub A and this is I sub B, then the current that enters this node, I sub A, has to equal the current that leaves this node. So that means that any current that flows through elements that are in series with one another is the same current. So this current is all the same because they're in series. Let's look at a KCL for a particular numerical example, a circuit, real circuit. And I'm going to look at this node right here. And I want to look at all the currents entering and leaving. And let me define this as being the one that maybe I'm trying to solve for, I. So let me look at the currents entering. We have I1 is equal to I3 plus I2 plus I. And that's just how to do the KCL at this node. In summary, we've introduced the Kirchhoff's voltage law and Kirchhoff's current law. We've applied the Kirchhoff's voltage law to parallel elements and found that two elements that are in parallel have the same voltage across them. We've applied the KCL to series elements and saw that any two elements that were in series had the same current going through them. And then we also solved a simple circuit using Kirchhoff's laws. In our next lesson, we'll do a review of impedance methods.